Hi everybody, and we're back to our last section in this lecture, and that is a very unique stress state, which is our thin wall pressure vessels. So what is a thin wall pressure vessel? So you need a thin wall, you need some pressure difference between an internal pressure and environment, and you need a wall thickness that's sufficiently small. So basically we say something is thin walled when our thickness is much less than our radius, or if our radius of our thickness, the ratio is greater than 10. If that's the case, we can reduce this three-dimensional problem to a two-dimensional problem. So basically, as you can see in this system here, we're ignoring basically stress across the thickness because we're basically just assuming that thickness to be effectively a surface. So the stress is not varying across the thickness, hence we are neglecting it. So we will not consider essentially those stresses and then those strain values. So it's a 2D problem, sigma 1, sigma 2. We can find those basically stresses by basically doing a cut for our free body diagram. Remember, we still have to be, some of my moments, some of my forces must be equal to 0. So if I cut along the longitudinal, I can look at essentially those forces here. So the pressure that's being exerted over the area here, and then the restoring forces, the stresses that are going out across that circumference, 2 pi RT. And you'll find that the stress in the one direction is delta PR over 2T. That's our longitudinal stress. We could do the same thing for a transverse cut to figure out our circumferential. So again, remember, we're going to have basically a delta P times an X times this 2R. And then basically a stress coming out in the other direction, which is going to be this little distance here. So basically sigma 2 times a delta X times a thickness here, T, and then times 2 of them because there's 2 of these little surfaces. So this will be our sigma 2 in this particular problem, our circumferential stress, and it's going to be our hoop stress. You can clearly see here that our hoop stress is twice as large as our longitudinal stress. And what you'll see, or what you'll find, is that our stress tensor will simply be, for this problem, it will be our sigma L, our sigma H, and then nothing else. Our strain tensor will be epsilon L, epsilon H, here. The hoop stress is twice as large as our longitudinal stress here, so our material will typically fracture like this. This circumferential stress is always higher, so it will fracture essentially across that, along that transverse cut. And if you want to figure out our expression for hoop, strain will just be 1 over E times sigma hoop minus mu times sigma L. So we're just using our equation 98 that we just went through previously. Epsilon L will be 1 over E times sigma L minus mu sigma H. And there we go. So we are already in a principal stress state. They're all already normal stresses, although more of that is going to come when we talk about next time. Moving on to lecture 5 and rotating and transforming stress states. So lots of Mathematica, but we'll see you there soon. All right, thanks. Bye.